Uh, so, good afternoon, everyone. Welcome to the second talk of the fourth day of the Limit Online Camp 2024. Today, we have with us Professor Radhika Gupta. She has done her BTech from IIT Bombay and then went on to become a program associate at the Mathematical Sciences Research Institute, Berkeley, USA. She did a PhD from the University of Utah under the guidance of Mlad and Westvina. She then went on to hold postdoctoral positions at Technion and the University of Bristol. She became a research assistant professor after that at the Temple University and is currently a reader at the IIFA Mumbai. She works in geometric group theory, group of outer automorphisms of a free group, and mapping classrooms. So I, with great honor, welcome Professor Radhika Gupta to present her talk on understanding symmetries.
Thank you. Thank you to all the organizers of Limit for inviting me to speak here. So today I want to tell you about, so I guess the title of my talk is What are groups? But the upshot is we are going to try to understand symmetries. Okay. So I'm going to ask a lot of questions. Feel free to unmute yourself and answer. I think that should work, but if it doesn't, then we will see if you can send me an answer on chat. Let me just quickly see how to, there is the chat. Is there an option to chat? No, it's not. Okay. Okay, I see someone's. Okay, I see it. So, okay. So maybe when I ask a question, you can answer me on the chat. I guess everyone can see the chat. Because I'll ask a lot of questions. Okay. So let's start. So I guess before I start, I just want to share two quotes, which I really like about math. So the first one is by von Neumann. He said, if people don't believe math is simple, that's only because they don't realize how complicated life is. And you like the more math you see in life, you will realize like there's so much structure in math, even though it's very difficult, but there's so much structure, it's much easier than handling your own life in a way. And this other quote is by Herman Weil, who says that symmetry is basically one of the ideas by which we as humans try to comprehend everything around us. Okay, so let's begin on our journey. I think there's a lag. So let me wait till the slide comes up. I'm going to wait one more second. So yeah, let's begin on our journey to understand symmetry. And then I'm just waiting for the next slide to show up. Why is it so slow? Right. Okay, this is faster, right? Yeah, so let me just do this instead of doing the presentation mode, I think. Okay. Okay, so here you can see I have lots of pictures on this slide. And maybe on the chat, you can share what kind of symmetries do you see. So I haven't told you what I mean by symmetry, but whatever symmetry means to you, if you can like tell me what are the kind of different symmetries you see on the slide. Or you can unmute yourself and speak up. Okay, so I got an answer. Translational, rotational. Right, so where do I see translation? I see translation at the, I see translation symmetry at the bottom here. And then I see rotation symmetry in the snowflake. I see rotation symmetry even in the starfish. Then there's bilateral, someone said. So bilateral, the butterfly has bilateral symmetry. Even this coffee, this like nice design on the coffee cup, that has bilateral symmetry. Here is translation symmetry. Mirror images, water images. So by mirror images, I guess you mean reflections. So yeah, so here I'm reflecting about this line. And maybe I can say even Taj Mahal is also like, I can also reflect about this line and it's still symmetric. Okay, so there's one question, would periodicity be classified as a type of symmetry? So yes, I guess I'm guessing you're talking about this picture, like this leaf on the right-hand side. So that is not symmetric in the conventional sense, but it's fractal. It's like symmetric if you keep zooming into it. So I would say it is also a kind of symmetry. So that's great. So there's lots of different kinds of symmetries here. And are we missing anything? Yeah, I guess this little origami down here. Oops. This little origami down here, like who knows how many symmetries does it have? Okay, somebody says the leaf has bilateral symmetry along the midrib. Yes, that's true. Thank you. The leaf does have this bilateral symmetry. And this origami downstairs, like it's some shape, and I can probably easily find some symmetries, but like listing all the symmetries is probably going to be hard. So that's one of the things we want to do today, like try to list all the symmetries of simple objects. So let's see. So what is a symmetry? I like this Calvin Hobbes cartoon. So Calvin used to have this transmogrifier where when you step inside that chamber, you turn some dials, and then you can become anything you want. Symmetries is the opposite. You step inside this chamber, you still like turn some dials, but you stay as it is. So that's what a symmetry is. You do some moves, but you stay the same. So like I said, say here, a symmetry of a space or an object is a transformation that does not change it. And a symmetry basically maps a space or object to itself. So let's look at the first picture that I've drawn. That little squiggle, that doodle that I've drawn, this has no symmetries. Right? There's like, I can't really flip or rotate or do anything nice. So another word for that would be I would say it has a trivial symmetry, or the symmetry which does nothing. So instead of saying no symmetries, I'm going to call it either trivial or do nothing. I'm just going to give it that name. And on the second picture, so again, I could do nothing. That's a symmetry. That's like saying be the identity map. And okay, so someone's saying 5-star symmetry. So this squiggle that I drew actually does not have a 5-star symmetry, because it's like, you'll see that my squiggle, like it's different here and here. But on this face, there is a flip symmetry. So instead of saying there's only one flip, I'm going to say there are two symmetries. One is where you do nothing, and the other one where you do a flip. Okay, let's look at more examples. Here I have a samosa on a plate. So I'm pretending my samosa doesn't have potatoes. It's just the matri. Okay, so sad. But let's say I'm allowed to, so it's basically a triangle. And if I'm not allowed to flip the samosa, okay, I'm not allowed to flip the samosa. And my question is, how many symmetries are there of the samosa? Assuming it's an equilateral triangle. So I'm assuming it's a perfect samosa, an equilateral triangle. So one person says there are 3 symmetries. Can you say 3 symmetries all through 3 vertices? Do nothing, and then 3 medians. 3 medians. I see, but by medians, you mean you're reflecting about the median? Yeah, so I'm not allowed to, my question was, you're not allowed to flip. We'll come back to this. We will consider the flipping in maybe like 2 minutes. But if I'm not allowed to flip, we can rotate, exactly. So I can rotate this, by 60 degrees, exactly. And then I get 3 symmetries. So let's say I rotate counterclockwise. So I've written the 0, 1, 2 just to help me write my rotation. So it would be 0, 1, 2 and 0, 1, 2. And then if I do another one, so I go here, and if I do another one, then I'm back to my original configuration. So I have these 3 rotations. So one click is called R. The other one is also R. The third one is also just rotation by 60 degrees counterclockwise. And what I see here is if I do it 3 times. So let's say R is rotation by 60 degrees. Then R square is rotation by 120 degrees. And R cube is rotation by, wait, did I do this correctly? Do I want to do rotation by 60 degrees or 120 degrees? Maybe that's, yeah, somebody said 60-degree rotation, but now I'm not convinced. Yeah, it's actually rotation by 120 degrees. So if I could rotate by 120 degrees, then 240, and then finally by 360, which amounts to doing nothing. Right? So that's easy. So now I want to just like write it more formally. So if R is rotation, okay, I did counterclockwise. So let's just say counterclockwise is 120 degrees. Then the set of symmetries is basically 1, R, and R square. So this one is do nothing, which I call the identity. So I'm thinking of these rotations as functions of my triangle, right? It's a function, R is a function from the triangle to itself. And so is identity, where you do nothing. So this set, C3, I'm calling it C3. So someone is saying I can think of these as complex vectors being rotated, sure. So there is an identity element, and I can compose 2 symmetries, right? I can do one symmetry, and then I can do another symmetry. I can do another symmetry, and then we saw that that's it. Like if I keep composing things here, these are the only 3 things I'm going to get. And there's also a cancellation happening here. So if I'm rotating counterclockwise by 120 degrees, I can also rotate clockwise. So for us, if R was counterclockwise, R square is basically I don't understand the question. Is R W? Yeah, so the next one is correct. Minus R is R square. So R square is, what did we say? Counterclockwise by 240 degrees, which is the same as clockwise by 120 degrees. And it is, so I won't say minus R, but I will say R inverse, just because I'm thinking of it as functions. And you don't write, if I have a function from R to R, I usually write F inverse and not minus F. So I'm going to say R inverse. So that R inverse is also in my set. So my set is closed under composing these things and canceling. Is R like cube root of unity? Yes. So if you were to actually write this in, if I were to put this thing, yeah, if I were to actually, no, I don't want 3 dimensions, my bad. Yeah, maybe at the center. Yeah. If I were to actually put this in the Euclidean plane, an equilateral triangle, then yes, these rotations will correspond to cube roots of unity. If you're thinking in terms of complex e to the I theta, then this theta is this I theta is basically a cube root of unity. Okay, so let's do squares. How many symmetries does a square have when you're not allowed to flip it again? So now can you give me a count? For triangle, we had 3. For square, we'll have 4. Easy, just do the 4 rotations. For a starfish, it will be 5. I think that's pretty easy. And then, okay, so now, like, since someone was wanting to do flips, so now let's allow flips. Okay, so now I have the 3 rotations, but like someone said, I have 3 more operations that I can do. I can flip about this median passing through 0. I can, flip about the median passing through 1, and I can flip about the median passing through 2. So I've introduced 3 more. Let's call this S1, S2, S3. I've introduced these 3 reflections. Okay, oops. Yeah, I guess I'm calling them S, S prime, S double prime. And now so I have some set of symmetries. And now my question is, can I compose these? Can I rotate once and then reflect and get something new? Yes. So answering the question, so we define symmetry as some operation that returns the same shape. Yes. So I've written some symmetries here. R is rotation, S, S prime, S double prime are these reflections. And I'm asking, can you compose these to get new things? So let's try some. So I've given you an exercise. So I want to do rotation. So let's see, I was thinking counterclockwise, right? So let's just remember. And what was S? Let's say S is S1. So maybe I'll give you 1 minute. If you have paper and pen with you, just try these two things and see if you get the same thing or not. In the first case, I'm first rotating, then reflecting. Second case, I first reflect and then rotate. Do I get the same thing at the end? Like, is the configuration of the 0, 1, 2 the same? So I'll wait for 1 minute. So I want you to compare, I guess, what I want you to do is compare these two. Not with the original one. Okay, I'm getting some no's that they're not the same. There's a question about period of a complex function. I guess that's not relevant to what I'm talking about. So maybe I'll not answer that question right now. Okay. Any more answers for what you get at the end of these two operations? Do you get the same thing or not? Okay, one more no. Okay, so everyone is getting 2 different things. Great. So let me do it with you now. So when I do counterclockwise rotation, counterclockwise is this way. So I get 0. And then I reflect by, it's okay. I guess maybe I should have clarified. When I say S1, I still, like secretly, this was the vertex about which the S1 flip happened, right? Or the S flip. Actually, I should have told you this. So maybe you got a different answer because I'm changing my notation. But let's say S is this flip. Okay, so I want to do this flip. So I get 1, 2, 0. And then here, I want to do the S flip first. So I have 0, 1, 2, and then I want to rotate counterclockwise. So I get 0, 1, 2, and they are not equal. So what we are saying here is that the order in which I do apply these symmetries matters. They're not the same symmetries. Okay. But let's see. Okay, let's try one more exercise. Where let me just say, for me, S is again this and R is counterclockwise. So can you try this? So I'm also going to try it with you. Yes. So I should have finished my sentence. Counterclockwise rotation by 240 degrees, which is the same as clockwise rotation by 120 degrees. Thank you. And then my question is, did I get, like, if I look at this composition, did I get a new symmetry or is this something I already had in my set? So what was my set so far? R, R square, S, S prime, S double prime. There. So let me draw the pictures again. This was S. I think this was S prime. And this was S double prime. Right, exactly. So when I do R square and S, I'm actually secretly just doing S prime. What I did was I just flipped around that vertex. So by composing these, I did not create a new symmetry. I created something I already had. So in fact, I can say that instead of writing S prime, let me just write, so I have to pick a convention. Let's write it like functions. So I do R squared first and then I do S. So S prime is the same as R square S. And you can check, I will leave this as an exercise, S double prime is the same as SR. So basically I can, is this what I was, yeah. So I'll leave this as exercise, this last one. So far I had S, S prime, S double prime, but S prime and S double prime, I could rewrite them just in terms of S and R. So I didn't need those extra symbols. They were basically just compositions of S and R. But my question still remains, can I do more compositions and get something even more different? Yeah, so someone says no, but then how do you check this, right? So again, some more exercises for you. So I've written some words. What do these mean? I want you to apply a rotation first, then a reflection, then a rotation, then a reflection. And I want you to check, do you end up with doing nothing or not? And so basically cook up your own words and try these things and see what you get. It's a fun exercise. Basically what you're trying to do is you found some obvious symmetries and you want to say they are all of them. There's nothing more. So a nice way to package this is by looking at this picture. So I think if you were to do this by hand, you would probably do the same thing. You start with you start with your original triangle, and then you apply a rotation. You get here, you apply another rotation, and if you apply another one, you know you'll end up with the same thing you started with. But then you're like, okay, now I apply S. After S, I can apply R. I can also apply R inverse. I could have applied R inverse, but I've drawn the arrow a certain way. Basically, I could keep applying R. So any combination that you want, you can read off in this diagram. And you'll see that just using R and S, you can get everything. And the set we came up with is actually everything. There are no more symmetries of this triangle. So this is a nice exercise to try again. So we call this set D3. It's called the dihedral group. Okay, and it still has the same properties. There is one operation which is do nothing. If you compose these symmetries in my set, you get the same things back. So if I compose two of them, I have the same thing back. Here I've written SR square is already in there, but you're wondering what about R square S? So again, you have to check. R square S has to be one of these things. I don't know which one right now, but it has to be one of those symmetries already. And there is also cancellation. Cancellation meaning for every symmetry, there is a way to undo it. So individually for rotations, you know how to undo it. For reflections, you just do the reflection again. And when you compose these things, again, you can undo them the same way. So, okay, so we have looked at two sets of symmetries. One was what I call the cyclic group of order n. You take a n polygon, then, okay, someone's already checked R square S is R. I'm not sure if that's correct. Or maybe it's, yeah, I'm not sure. Yeah, I trust you. Okay, so we have the cyclic group of order n, and then we have the dihedral group of order n. And Cn is smaller than Dn. Okay, so here is another question for you. So here I have the Ashok chakra. And my question is, how many rotational symmetries does it have? I have one answer. Let's see if there's more answers. So I guess you need to know how many spokes does the Ashok chakra have? 24. Great. So everyone knows there are 24 spokes, right? Because I have to take, by my rotational symmetry, I have to take one spoke. I have to take a spoke to another spoke. Awesome. And then how many reflection symmetries are there? Also 24. Okay, well, one person said 12. Another person said 12. More 12. Okay, I'm getting lots of 12s. Let's see. So I can reflect about, let's see, I can reflect about this line. And then how many such lines are there? There are 12 such lines, right? Because there are 24 spokes. So there's 12 such lines, but I can also reflect between the spokes, like someone said on the chart, and that gives me another 12. So it is 24. Yeah, so it's a fun exercise. When you see a nice shape, you should try to think about how many symmetries it has. Okay, so now let's make things a little more abstract. We've done some very nice examples, which is how you should, like whenever you see a result in math, you should try to come up with some examples to make sure you really understand things. And this is how math research is done. Often, not always, but often, that you think of you see some phenomena, you see some examples, and then you try to generalize things. Right. So let me tell you what is a group. What we've seen so far are examples of groups, but formally, what is a group? So a group is a set with an operation. So it contains the identity element, which is the do nothing. And if you compose two elements, you end up in the set back. So this is like saying if you compose two symmetries, you get a symmetry again. If my set is a set of symmetries, if I compose them, I get a symmetry again. There is also an inverse, which means like if you do a symmetry, there's a way to undo it. And the last one is associativity, which is slightly more mysterious, but let's not worry about it for now. But you need this property also to call a set a group. Okay, so remember three things. You need a do nothing or identity, such that when you compose your element with the identity, you get the element back. Then there is composition. When you take two things, apply this operation, you end up in the same set. And for every element, there is an inverse. So that when you compose those two, you get do nothing. So let's do an example. So I'm looking at the set of natural numbers where I've included 0. And I'm asking you, is this a group with addition? So let me quickly write down things I need for group. So I need an identity, which is like do nothing. Or let's make, for me, like I write the identity as, let me write it as E. Okay. Then I need composition, which says that x dot y is in my set S. And then inverse, which means for every x, there is y such that x dot y is the identity. Okay, so I'm getting a lot of answers which are saying that it's not a group because there is no inverse. I cannot invert because I'm doing this thing with addition. So what's the identity here? The identity is the number 0, because if I take a number n plus 0, 0 is same as 0 plus n is the same as n. Composition is fine. If I add two numbers, I get a natural. If I add two natural numbers, I get a natural number. But then if I take n, I know I need minus n to make it 0, but minus n is not in my set. So good, this is not a group. Okay, let's try another one. So now I give you integers. Okay, so now I throw in the negative numbers as well. And I'm still looking at the addition operation. So it will be a group now, because that was the only issue I was facing earlier. With subtraction, it's actually not a group because of associativity. But because it's a mysterious property, I'm not going to dwell on it. You can think about this. What about if I again look at the set of integers, but with multiplication now? Is this a group? So if I take a number n, I need to multiply it with 1 to get it back. Right. So correct answer, there are no inverses. So again, if I multiply two numbers, I still get an integer back. But I need to multiply it by 1 over n to get 1. But I don't have 1 over n in my set. So this is also not a group. Okay. So I guess if you wanted a group with multiplications containing z, then you can look at rational numbers. Any questions so far? Awesome. Okay. Okay, let's look at, I'm going to do some more examples. Let's look at this thing called permutation group. And there's a reason why it's also called a symmetric group. Okay, so what is a permutation? So let's do an example first. So I'm just looking at a set of two elements, 0 and 1. And a permutation is basically permutation is just you. Yeah, that's a good question. Thank you. In rationals with multiplication, it's actually, I have 0, so that causes problems with calling it a group. 0 will not let me make it a group. But if I remove 0, then it will be a group. Yeah, thank you. Right. So what is a permutation? Is a one-to-one map from X to itself. So I have the identity permutation, which doesn't permute things. And I have this other permutation, which sends 0 to 1, 1 to 0. Right. So those are the two permutations I can have of this set of two elements. And now now I can permute permutation. Sorry, I can compose permutations, right? If I have a permutation, if I have another, I can do the first permutation and then I can do the second permutation. I can just compose these functions. So if I do f compose with f, so I swap 0 and 1 once, and if I swap them again, I end up with the identity. So the number of permutations of this set is actually just 2. How many elements are in this group? Just 2 elements. And the fact that it's a group, you can, yeah, you can check. But now let's think of a set of 3 elements. And how many, yeah, so here's a question, how many permutations of 0, 1, 2 are there? Okay, great. Everyone's saying 6. So that must be correct. It's not a proof, but that is correct. It is 6. And so since you're all saying 6, you all know how to do it. But the way I am thinking of it is using the same diagram I was using for the dihedral group. So basically, if I do a rotation, if I start with 0, 1, 2, and if I rotate, it becomes 1, 2, 0, or whichever way I'm rotating. So I can even think of these permutations. And if I do a reflection, then I'm keeping 0 as it is, but I'm just switching 1 and 2. Right? So these are, the 6 triangles that are drawn here are basically giving me the 6 permutations of 0, 1, 2. So it turns out, in this case, the group of permutations is the same as the dihedral group, just for 3. And then the question is, like, is that true for, if I look at permutation of n elements, is that always the same as the group of symmetries of an n polygon? Maybe, can you think about 4 and give me an answer? Is D4 the same as S4? Okay, yeah, my question is, let me write it in different color. My question is D4, which is the group of symmetries of a square and all the symmetries, rotations and reflections, is that the same as the permutations of 4 elements? Okay, so there's 2 no's, there is some no, or there's maybe no. Okay. Yeah, mostly everyone thinks that the answer is no. And it's correct, right? Because when I'm doing the group of symmetries, if I see if I can make this bigger. If I make the 0, 1, 2, 3, when I'm doing permutations, I could send 0 to, let's see, which one do I want to do? I can do 0 to 2, 2 to 0, but 1 and 3 can stay the same. No, that's okay. That's this. That's this reflection. So this reflection sends. Oh, but I can't do this. Sorry. If I do. What do I want to write this? 1, 0, 0, 1, 2, 3. Right? Using a square, I can never send 0 to 1, 1 to 0, but 2 to 2, 3 to 3. That's the one that I can't do on a square. Like on this square, it's impossible for me to switch these two, but not switch these two. But as a permutation, I can always do that. Right? So So for 3, even though like I had 2 different ways of coming to the same group, actually for higher ends, these are different groups. But the dihedral group is contained in a group of symmetries. And in fact, every group is contained in like I have contained in quotes because you have to say what that means. But in some sense, every group is contained in a symmetric group. Okay. Okay, so that was a lot of concrete exercises we did. And now I want to I'll move a little fast because we're not doing to do concrete exercises, but I want to give you some overview of symmetries. So this is something you can explore a lot, symmetries of tilings. You've probably already heard about these. So there's something called free symmetries. Whenever you go to a temple, or even like if you look at your mom's sari, you'll see these borders and you'll have different symmetries in those borders and in these temples. So there's actually like 12 kinds of free symmetries. 7 kinds of free symmetries. And so these are like one-dimensional symmetries. And then there are 2-dimensional, you see wallpapers. And then here I can ask you, what are the symmetries of this design? So one obvious one is like there's a vertical translation, there's a horizontal translation. You're probably seeing some reflections. Then the hard question is, can you list all the symmetries? Or can you give a nice compact way of saying all the symmetries? Like even with just translation, right? Maybe let me do one thing. Like even with this first picture, with translation, I can translate by one step. I can just not translate. I can translate by one step. I can translate by 2 steps, 3 steps, 4 steps. I can translate backwards by 1 step, backwards by 2 steps. So I'm basically getting the set of all integers under addition. So that's a nice compact way of saying what are the symmetries of this first pattern. And it's all generated by like just saying one step is enough to say that I can do any steps. So that's a nice compact way of saying all the symmetries of the first picture. So these are hard questions, coming up with symmetries of complicated patterns. Yeah, right. So for wallpapers, there's actually only 17 different wallpapers. So any wallpaper you see can be classified as it can only have possibly 17 different symmetries. Sorry, not 17 different symmetries. 17 different kinds of symmetry groups, which I think is mind-boggling. Because you can draw like all sorts of intricate designs and things, but mathematically, like it's a theorem. There's only 17 different wallpapers. And then Penrose came up with a tiling which has no symmetry, which is also weird. Sorry, which has not no symmetry, which has no translational symmetry. Like you can't translate and get the same thing. There is no translational symmetry. Here you do have rotational symmetry. You can rotate about these points. But all this is to say, symmetry groups can be very difficult to describe. It's not an easy thing to do. If I hand you a random object and ask you for all its symmetries, like a question, a very famous question is, whose answer is known, is like Rubik's Cube. Actually, solving a Rubik's Cube amounts to understanding its symmetries, for instance. So you understand some small groups, but then you are a mathematician and you want to know, wait, how many groups are there total? I want to know in the big picture, how many groups are there? And if somebody hands you 2 groups, how do you tell them apart? Like we did for DN and SN, right? There we were just able to say they are different because they had different number of elements. But if they have the same number of elements, how do you say actually they are 2 different things? So one of the, I think this is like a massive effort by mathematicians over, you can see how many years, over many, many years, where they try to classify all finite. So I've been talking about finite groups mostly, except like the translation was an infinite group, integers were infinite groups, but these rotation for polygons, these were all finite groups. So there's a complete classification of finite, something called simple groups. And it was a massive collaborative effort. It was not one person who just thought of it or spent his or her life doing it. Like hundreds of mathematicians came together and solved pieces of it and put it together. It was a massive effort to classify all of them. So now basically there is a list, and any finite group you come up with is one of the groups in this list. But then you're like, where did all this start? How did it all start? Like, how did people start thinking about symmetries? I think people were thinking about even before. Like somehow inherently we see symmetries. Maybe even cave people were thinking about symmetries, even though they didn't have the language to talk about groups and stuff. So when did this language of groups start? It actually started by someone trying to solve polynomial equations. I'm sure you've all done this in school. Quadratic equation is something we learn to solve very early, right? We also know a formula for solving a quadratic function. It's like minus b plus minus square root of b square minus 4ac by 2. Okay, that's one formula you'll never forget. Because in school, you're just like made to learn it so much. But so what? Like, what does this have to do with symmetries? What this has to do with symmetries is that the solutions, if you look at these two solutions, there is a very nice symmetry in the two solutions, right? They only differ by this plus minus sign, and all the other terms are the same. So I'm talking about symmetry in a different sense. There's no shape here per se, but I still have a set. I have this set of solutions, x1, x2, and there is a symmetry in that solution set. It's hard to like name that symmetry, but you'll agree there is some symmetry here. Okay, very nice. And then you've probably also learned this in school. You probably learned some ways of solving cubic equations, right? Like there's the hit and trial method that I remember. You can look at the factors of b or a by, let's say a is 1. Then you can look at the factors of b and try to see if you can find a solution. And actually, if you go to Wikipedia, you'll see there are formulas which actually look very ugly, which is why nobody forces us to learn that in school. But you can find formulas for solving cubic equations. And interestingly, also for the equations of degree 4, there also exist, I think, some formulas for solving equations to degree 4. But they're so complicated, nobody really bothers to track them down. Then the question is, what about degree 5? Can you also write down formulas for solving a polynomial of degree 5? Oh, you had a lecture on this right before this. That's awesome. Okay, yeah, so I'm not going to give you a lot of details about this, but I think what I was going to say is Galois was the first person who thought about this. And he showed that you cannot write a formula for degree 5 and above polynomials. And someone saying Abel and Ruffini, maybe they provided more details. I don't know the full history, but the ideas originated with Galois. And basically the way he tried to show that you cannot find formulas for polynomials of degree 5 and above is by trying to look for symmetries in the set of solutions. And you will see Galois did not live very long. He died when he was 21, but he basically, group theory was born with Galois. Like Galois is like the father of group theory. So even in like, yeah, so you should go read about his life. It's very sad that he died in a duel. If he was alive, or who knows how much more interesting math he would have come up with. Yeah, so basically I'm saying something as simple as like solving simple, which we think is simple because in school we learn to solve some polynomials and we are fairly comfortable with polynomials. We think we are comfortable, but they're actually very complicated, and like somehow that's where group theory has its origins, like formalizing symmetries. And groups show up in basically every field of mathematics, not just mathematics, physics, chemistry, biology. Every time you need to understand, yeah, you should not fight. every time you need to understand symmetries of something, you are basically doing group theory. Like I actually, yeah, my area of research is called something called geometric group theory. So there's some geometry and there's some group theory. And the way I try to understand my geometry is by trying to like find groups associated to that, and the vice versa. If I want to understand a group, I try to associate a space to it and try to understand that space so that I can, basically I try to, somebody hands me a group and I want to view it as a symmetries of some space. Like that's how, there's a question, is knot theory related to group theory? In some manner, not. I guess knot theory is, if you're thinking like formally, it's a branch of topology. But when you're studying knot theory, you're using groups everywhere. You're using abelian groups. Yeah, group theory is like you don't even, like even as a topologist, I don't even think that I'm using a group sometimes. And I think I want to just end by telling you about the sphere packing problem. What's the sphere packing problem? So in dimension two, like how do you pack the most oranges in a box? And I think what I've shown is the best. That's the best arrangement, which people, I think people knew that for a really long time, but it was proved in 1890 by someone named Thue, and then tried the hexagonal packing. And then in 3 dimensions, Kepler conjectured that there is, like, the way the oranges are shown here, that's also some kind of hexagonal, some 3-dimensional version of hexagonal packing. That's the most efficient way of packing. Basically, if you're an orange seller, you want to fill a box with as many packages, as many oranges as you want. Right? So I guess there are more names for these things: cannonball theorem, pyramidal number, and so on. So Kepler conjectured this in 1611. And then Thomas Hales came up with a proof in 1998. But I think his proof was very complicated. There were lots of cases. And it took a really long time for people to understand that proof. So in mathematics, you might come up with a theorem and proof, but unless you're able to explain it to people, or people agree that, yes, we believe this proof, people don't start calling it a theorem in some sense. And then, yeah, so Thomas Hales, then eventually he wrote his proof on a computer, like it was computer checkable. So that was in 2014. So even, it took him a long time to make it computer checkable, the whole thing. There's a lot of cases, I think, in his proof. And then in 2022, the Fields Medal, which is the Nobel Prize of Mathematics, was awarded to Marina Biazowska, who did this sphere packing problem in dimension 8 and 24. And even in that, when she was doing this sphere packing theorem or result, some group theory showed up. I think that's, I mean, I can't say more about what kind of group theory showed up, but so E8, I've written it, I think I didn't get a chance to point it out earlier. This is one of the finite groups in the list. Right, I told you there is there's a classification of finite simple groups. So this is one of the groups in that list, and it shows up in this sphere packing problem. I guess sphere packing problem has why 8 and 24? That's a good question. I think somehow these 2 dimensions, 8 is like, what's the word, quaternions. There is something called quaternions, which end up giving you a lot of structure to 8-dimensional geometry. 24, I'm not so sure. 12, I don't know exactly what's special about 24 and 12. With 8, there is something called quaternionic numbers or quaternionic geometry that plays some role. And I think I will stop here. Thank you for listening. What are the prerequisites to start group theory? So I think if you want to, I don't remember if you are you in high school or college? I don't remember. High school, right? So one thing you can start learning is something called modular arithmetic or modular groups. Modular groups are something very easy and fun to start with. And you don't need any prerequisites for starting to learn modular groups, in fact. Yeah, so modular arithmetic is number theoretic, but there are also modular groups. Basically, these group of rotations that I was talking about, I was using the numbers 0, 1, 2, because that's like Z mod 3Z. That's the group Z mod 3Z. And yeah, I don't have a reference in mind. Dammit and Foot is a good book. I mean, that's what people learn from in undergrad, but I don't know if it's a good book if you're in high school. But I don't know how much you'll be like the language is a little hard, I think.
Thank you, ma'am, for the wonderful talk. If anyone has any more questions, they are free to ask.
Okay, somebody has a question about how many reflection symmetries are there in the Ashok Chakra. So I think my solution was I can reflect about this red line, and there are 12 of those red lines because we agreed that there are 24 spokes, which means there are 12 red lines. But I can also reflect in the middle of the spokes. So there is a green line, and again, there are 12 of those green lines. I don't see where the infinitely many rotations will come from. Yeah, this is basically, if you want to make this more abstract, I'm looking at a 24-sided polygon. Right, so if you don't like thinking about the Ashok Chakra, like it's confusing, just think of a 24-sided regular polygon and try to see. And like in a square, you have these diagonal reflections, and then you have these opposite side reflections. Oh, but because you have space between the spokes, but you can't put infinitely many lines there, right? You have to, since you're looking for symmetries. So basically, if let's say I have angle, let's say this is the space, these are my two spokes. And if you put a line, so I want to put a line in the center so that these two angles are the same. But if you put a line and then I want to reflect, so the spoke 1 goes to spoke 2. But if you put a line very close to spoke 1 and reflect about it, then the two spokes will not go to each other. Yeah, so like someone said 1/4 and 3/4. So then you won't be mapping spokes to spokes. For symmetries, you have to get the same object at the end. Okay, thank you very much. And thank you for answering a lot of questions. That's always nice when the audience interacts. So I appreciate you answering things.